Hi everyone, welcome back. So myself Ayush Tripathi, working as a mentor and problem setter at Geeks4Geeks, and I welcome you all to this post-analysis video of last weekly contest 170. So the first greedy problem is find the smallest, and in this problem you will be given an integer n, and you need to find the smallest positive integer x such that x is greater than 0 and it is basically very obvious because here it was clearly mentioned that the smallest positive integer and the value of n and x must be equal to 0. So let's see how we can solve this problem. So let's consider this as the binary representation of n, and we all know the weight distribution. So the LSP has the minimum weight, which is 2 power 0, then 2 power 1, 2 power 2, then 2 power 3, and so on. The current weight is double of the previous weight. So we need to find the smallest positive value of x such that the value of x and n must be equal to 0. And we all know the basic AND operation. 1 and 1 is equal to 1, and this is the only case when the result is 1, and the value of 1 and 0 or 0 and 1 which is equal to 0. Cool. So consider this particular example. So here the value of LSP is 1, so we cannot make it 1, we cannot make it 1, so let's just make it 0 to have the result as 0. Then the next bit is also 1, so we cannot make it 1, otherwise the value of AND would be non-zero. So we are restricted to make it 0, so 0. Now the next bit which has the minimum weight for as compared to all the upcoming bits, so I will make this bit as set. So here we have 0 and 0 and 1 which is equal to 0. So I will just simply make this bit set, and the result would again 0, and since now the value of x becomes greater than 0, so I just simply immediately stop at here. So and the remaining bit I will just simply make it to 0. Now the value of x is greater than 0 because it has one set bit, and this is the minimum value of x, so satisfy all the conditions. So yeah, this is the complete explanation. Start traversing from LSP to MSP. Once you got a bit as 0, just simply make a bit set in x and stop it over there. That was the minimum value of x. So here is the implementation. Instead of using a variable name as x in my implementation, I have used p. Then I iterate over all the integers from 0 to 30, and because the value of n can only be up to 10 power 9, and 10 power 9 has somewhere around 30 bits, lesser than 30. Then here if it is 1, if the bit is 1, then we cannot make it set, so just simply skip the bit. But once I got that the bit is 0, bit I is 0, then I will just simply make this bit set in variable p, and then I will break this loop because now it is greater than 0 and the end value is also 0. So here I'm just simply returning the smallest value of p. The time complexity is a constant, which is 30 iterations, and the space complexity is also constant. So this is the complete explanation for the first problem. So this is the second problem of the contest, validate a distribution, and this problem is based on dynamic programming. John and Bob are two brothers who want to divide n candies, each with the sweetness value that may or may not be distinct. That is, values of the array may or may not be distinct. And since Bob is the elder brother, he insists that his total sweetness should be exactly twice the total sweetness of John's candy. And we need to determine if it is possible to distribute the candies such that Bob's total sweetness is exactly twice that of John's total sweetness. And we have to return 1 if such a distribution is possible, otherwise we have to return 0 if such configuration does not exist. So let's see how we can solve this problem. So let's just say array is named as A instead of sweetness, which is given in the problem statement. So first I will find the total sweetness of all the n candies, that is a sum of all the indices values from 0 to n minus 1 a of I, and once I get the total sweetness of all the n candies, then I will just simply divide it by 3. So total divided by 3 plus total divided by 3 and plus total divided by 3. and if you add these two values together, these three values together, you would get total, that is sum of all the n candies, because the entire array sum is constant. And the Bob's sweetness must be twice of John's sweetness. So 2 into total divided by 3. This is the total sweetness of Bob's candy, and the John's sweetness would be total divided by 3. Cool. So now we just only need to check whether there exists some subset in the array A whose sum is equal to total divided by 3. You can also check for 2 into total divided by 3, which is the sweetness of Bob's candy, and since the entire array sum is constant, so the remaining person would have a subset sum is equal to the leftover sum. So let's just fix this one, total divided by 3. Now I just only have to check whether it is possible to select some subset from the array A whose sum is equal to total divided by 3. And this is very standard problem of a dynamic programming, subset sum problem. So let's just first define a state. First define a state f of x comma y as whether there exists some subset in the subarray from x to n minus 1 with the sum equal to y. So this returns me a boolean value, and it simply defined as whether there exists some subset in the subarray starting from index x, and it goes till n minus 1, where n is the size of array A, and here I am considering zero based indexing, so that's why from 0 to n minus 1 with some y, and here this x is index, and this y is a target sum, is a target. So what would be my answer? What would be my answer? I would just simply call the function from the main function f of 0, that is some subset in the subarray from 0 to n minus 1, the entire array, and comma total divided by 3, that is John's total sweetness. And what would be the transition? So for every element, for every index x, I have two possibilities, that is include or exclude. So f of x comma y. So f of, I would just simply make a call for the remaining subarray, which is starting from x plus 1, and the target would remain as it is. This is an exclusion part. For every index, I have two options, whether I would include in the subset, or I would just simply exclude from the subset. So this is an exclusion part, exclude. And if I include, then from the remaining subarray, I wanted to form a sum y minus a of x. So x plus 1 take me to the next index, because we cannot include the same index again and again, and then y minus a of x. Very straightforward. And to make this recursive call, this is an inclusion part, include. And to make this recursive call, we need to check a condition whether the required sum is greater than or equal to the value at index x. Then only I would make a call. So if y is greater than or equal to a of x, then only I will make this call. And if it is exceeds the target, then I cannot include the value at index x. And what would be my base case? So if the value of x is equal to n, that is v reaches out of bound. So in that case, we just only have to check whether the value of y is equal to 0 or not. And if it is equal to 0, then I will return true, because from an empty array, it is only possible to make some 0, and other than 0 is not possible. So if the value of y is equal to 0, then I will simply return true. So return true, that is 1. And if the value of y is not equal to 0, that is the else part. So in the else case, I will just simply return false. It is not possible to make some y from an empty array. So return 0, that is false. Cool. So yeah, this is the complete explanation. Let me show you the implementation here. So this is the method that you have to complete, and given parameter n, that is size of the array, and this array. So first I will calculate the total sweetness, and if it is not divisible by 3, then it is not possible. So simply return 0. Otherwise, our target would be total divided by 3. And here I am having a DP array for a memorization purpose, and this is of size n multiplied by target plus 1, and simply setting all the values to the -1, a simple memorization step. And then I'm calling this a recursive function from index 0, that is subarray 0 to n minus 1, and this is my initial target, and then these two array for the reference purpose. So this is my base case. if I is equal to n, that is if I reaches out of bound, and if target is equal to 0, then return 0, and if it is not equal to 0, then return. If target is equal to 0, then return 1, that is true, and if it is not equal to 0, then return false. So this is simply a boolean expression, and here I have done a memorization part. If I already know the result of this state, then do not compute it again, simply return the result, and otherwise I have a boolean answer variable, and this is an exclusion part where I do not include the element at the current index. So simply take me to the next index, and the target would remain as it is. And then this is an inclusion call where I will include the element at index I. So if I will only include the element if the target is greater than or equal to the value. So here I am taking or, because we just have to return the answer if it is possible in any way. So answer or this recursive call, inclusion recursive call, take me to the next index, and now the target would reduce by ARR of I since I have included the element, and then I will just simply store this answer in a DP vector, and finally I would return this answer. So let's just try to submit this. Cool, successfully submitted. And what is the time complexity? So here the value of n can be up to 100, and the value of sweetness is also up to 1000. So let's just discuss the time complexity. So the value of n is up to 100. So let's consider the worst case scenario. Value of n as 100, and the value of a of I is up to 1000. So consider the maximum value of a total where all the indices are having the maximum value as 1000. So it is equal to 100 multiplied by 10 power 3, that is simply 1000, which is equal to 10 power 5. So 10 power 5, and the target, my target, was initially equal to total divided by 3, that is 10 power 5 divided by 3. And since I have done the memorization part, so the time complexity, it is equal to n multiplied by total divided by 3, which is somewhere around 10 power 7, which is a feasible time complexity. And the space complexity is also the same because of the memorization dp vector. So yeah, this is the complete explanation for the second problem. So this is another problem on dynamic programming maximize expression. In this problem, you are given a 2D matrix of a dimension n cross m containing positive integer values, and your task is to remove exactly one row and one column from the matrix, resulting in 4 submatrices: top left, top right, bottom left, and bottom right. And here are the definition of these 4 submatrices. And the goal here is to maximize the value of this expression, that is sum of cell values in the top left submatrix multiplied by the sum of cell values in the bottom right submatrix plus sum of bottom left submatrix multiplied by sum of top right submatrix. And we have to optimally select the row and column which we will delete to maximize the value. And for the first sample input, the expected output is 17, which is the maximum value that you can get by deleting the second row and second column of the initial matrix. So how we can solve this problem? Not just only in this problem, in all such problem where you have to maximize your answer or minimize your answer, there could be only 3 possible approaches. The first one is greedy solution, where you will propose some greedy approach and claim that your answer depends on few states and you will explore only those few states. And for this particular problem, I won't be able to find any greedy approach. So the next is binary search, and also for this particular problem, I won't be able to find any monotonic predicate function which is necessary and sufficient condition to apply binary search. Now the third one, recursion. Recursion means I will try out all the possibilities, I will explore all the possible state and will select the state which will give me the maximum answer. So I will delete each column, and for each column I will try to delete each row, and then we'll find the value of the expression, and we'll select the maximum answer that we can get. So let's just first draw some observation. So the very first observation, it's never optimal to delete boundary column or boundary row, because in that case the sum of at least 2 submatrix would be 0 and your entire expression will evaluates as 0. But for this problem, it's always possible to achieve answer greater than 0, because here the number of rows and the number of column would always greater than or equal to 3, and the value at each cell is at least 1. So it's always possible to achieve answer greater than 0. So never optimal to delete boundary row or boundary column. So this problem uses a very standard technique of DP on matrices, where I will first pre-compute the sum of cell values in each rectangle. So let's just first form a state, and then I will find the recurrence relation to compute the value of each rectangle formed by a diagonal starting from coordinate 0, 0 to coordinate I, j for all the possible values of I 0 to n minus 1, where n is the number of rows and j is the current column for all the possible column values 0 to m minus 1. So yeah, this is the state. Let's say dp of I, j simply represent the sum of cell values in the rectangle formed by diagonal starting with the coordinate 0, 0, that is a top left cell, to coordinate I, j for all the possible values of I and j. So let's say this is row I, and this is column j. So this is the cell, and we are interested to find the sum of cell values in this rectangle. So I have just separated out this submatrix or a rectangle, whatever you say, and this is row I and column j. So how we compute the sum of cell values in this rectangle? So that is a dp of I, j. So dp of I, j, it is equal to arr of I, j, basically the value of this cell, and arr is the matrix which will be given to you. And let's say we already know the sum of cell values in the top rectangle, this one. So this simply means plus I will simply add the value of top rectangle dp of I minus 1 previous row and the same column, the sum of cell values in the top rectangle. And let's say I already know the sum of cell values in the left rectangle, this left rectangle. So this is simply equal to plus dp of I same row and the previous column I to j minus 1. So top rectangle dp of I minus 1 j, and left rectangle dp of I comma j minus 1. And since I have added the contribution of this segment twice, so I have to subtract it once. So this simply means minus dp of I minus 1 and j minus 1. And this is the complete recurrence relation, and this is very standard recurrence relation of dp on matrices. And what would be my base case? So this entire first row is my base case, because for these row I do not have any cell which is its top. Basically for these rectangles I do not have the top rectangle, so this would be my base case. And similarly the first column is also my base case, because for these rectangles I do not have any rectangle on the left of it. So let's just now assume we know the sum of cell values in each rectangle for all the possible values of I and for all the possible values of j. So how we find the answer? So the next thing is to iterate for all the possible values of I and for all the possible values of j. And apart from the boundary row and the boundary column, that is the value of I starts from 1 second row, and the value of j would also start from 1, that is the second column, and it goes till last second row and the last second column, that is I is equal to 1 to n minus 2 and j is equal to 1 to m minus 2. Cool. And for current value of I comma j, how I will compute the sum of 4 sum matrices. So first let's just compute the sum of cell values in the top left submatrix. So top left, so this is simply equal to dp of, so here I have fixed I and j, that is I will delete row I and column j. So this is simply equal to I minus 1 and j minus 1. Very straightforward, because this is the definition of dp value. And so yeah, this is the sum of cell values in the top left submatrix. Now how I will compute the value of sum of cell values in the top right submatrix. So let's say top right. So for this thing how I will compute this thing? So to compute this value, I know this rectangle value. So this is simply equal to dp of dp of dp of I minus 1 and m minus 1, and basically here the last column is at index m minus 1. Cool. So yeah, this is the rectangle value, and minus from this rectangle, I have to subtract this area. I have to subtract this area so that I can easily get the required portion. This problem is based on a principle of inclusion exclusion, which is a very basic thing. So this green part, which is a dp of I, and which is not I, but it's actually I minus 1. Yeah, I minus 1, and simply j. So this is the top right portion, sum of cell values in the top right sub matrix. Cool. Now how I will compute the value of bottom left sub matrix, So for this thing I already know the value of this rectangle, this complete portion, and this is simply equal to, let me write it here. So bottom left, and it is equal to dp of n minus 1. Basically the last row is at index n minus 1, and then previous column j minus 1, and from this portion I will subtract this area, this one, so that I can easily get the required portion, which is this one. So dp of dp of I and j minus 1. Very straightforward. Cool. And in this way I will simply get the sum of cell values in the bottom left submatrix. Now we just only need to find the sum of cell values in the bottom right submatrix. So bottom right, and basically this part, and for this thing, how I will compute the value of this rectangle. So from this rectangle, which is the sum of entire initial matrix, so it is simply equal to dp of n minus 1. Here I am considering the zero based indexing, so n minus 1 and m minus 1. This entire part, I will just simply subtract. This portion. I will simply subtract this portion. So which is equal to minus dp of what we can say. It's simply I and m minus 1. Cool. And then I will simply subtract this portion. I will simply subtract this area, this entire part, and this is simply equal to minus dp of n minus 1 to the last row, and j would be remain same. And since I have subtracted this portion twice, so I have to add it once. A very straightforward principle, inclusion exclusion. So plus dp of I minus 1 and j minus 1. So it's not I minus 1, it's basically ij. dp of I and j. So this is the value of cells in the bottom right submatrix, and once you get these values, then just simply put them in an expression and find the value of the expression, and always take the maximum answer. Cool. So yeah, this is the complete expression. Let me just show you the implementation here. So here this is the solution class which we have to complete, and inside this solution class you have to complete this get max method, which simply takes a 3 parameter, and basically the number of rows and the number of columns and the initial matrix mat. So first here I have created our temporary 2D array dp, and just for an educational purpose I have created an extra array, but you can also use the same matrix which is given to you. So here the value of first cell, that is dp of 0 comma 0, which is equal to arr of 0 comma 0, or you can say arr or mat, whatever it is. And then these two are my base cases. Then the recurrence relation, first I will compute the sum of cell values for each rectangle starting from 0 comma 0 to coordinate I comma j for all the possible values of I and j. And then here I have initialized the answer with 0. Then I iterate over all the rows starting from the second row to the second last, and for all the columns starting from the second column to the second last column. And then these are the values of the submatrix, and then this is the value of the expression, and always take the maximum answer. And here I am finally returning this answer. So let's just try to submit this. So here I am having the same solution. And the time complexity is simply n into m, because we are iterating over each cell. And the extra space is also n into m, but since you can also omit this extra space by using the same vector which is given to you. But since it is an educational video, so that's why here I have created a separate array for a better explanation. Cool. So yeah, this is the complete explanation for this problem. So this is the last problem of the contest, 2 maximum. In this problem, you are given a tree with n number of nodes, where nodes are numbered from 1 to n, and the root node will also be given to you. And there is m independent queries. For each independent query, you will be given a node number, and you have to delete a subtree of that node. And the answer for the query is the 2 maximum node number in the remaining tree. So let me explain you the first example. And if there does not exist 2 maximum node numbers, so in that case you have to place -1. So for the first sample input, this is the underlying tree structure, and these are the m queries, and the query array is named as request. So let me explain you on a whiteboard. So the first query is for node 2. So we have to delete the subtree of node 2, and in the remaining tree, the 2 maximum node number are 4 and 6. So the answer for the first query is 4, 6. Then the second query for node 4, and we have to delete the subtree of node 4. So this subtree we have to delete, and the 2 maximum node numbers are 5 and 6. So the answer for the second query is 5 and 6. So I hope the problem statement is clear to you. And this problem can be solved with the help of Euler tool. The idea for the Euler tool is to flatten the tree into an array, because performing operation over linear data structure is comparatively easier than over non-linear data structure. So let me just give you a brief overview of Euler path and Euler tool and Euler circuit. So Euler path is a path that goes through every edge of a graph exactly one. I will visit every edge exactly one time, and this thing is called as a Euler path, and basically all the DFS traversal are the Euler path. Then Euler circuit is a path that begins and ends at the same vertex. So you can consider as a cycle, because whenever I make a call to the function, then I will return back to the parent function from the same function itself. It's kind of a recursion when it's fold itself and unfold itself. But here the agenda is to discuss a Euler tool, not Euler path, not Euler circuit. So let's consider this tree, because the Euler tool is only applicable on trees. You cannot apply Euler tool on a graph which has a cycle. And we all know all the trees are cycle, but all the trees are not all the graph are trees, but all the trees are not graph. So consider this tree, and here I am writing a DFS traverser. So there exist multiple DFS traverser, but here I am writing one of those multiple DFS traverser, and we all know it depends on order of neighbors. So starting with the root node, first I will make a call and visit this root node. So I will just simply print 1 here. Then let's say we make a call for 2. So print 2, and at the same time I will also assign the time in and the time out for these node. So let me just first print the DFS traverser, and then I will assign the time in and the time out values for each node. Time in basically means when I enter to the DFS function, I will assign a time in value to the node, and when I return back to the parent function, I will assign timeout value to the node. So from this two, let's say we make a call for node 4. So just simply print node 4. Here I'm just simply printing one DFS path, and then simply return back to the parent function from this 4, because we do not have any child of this 4. Then from this 2, there is one unvisited child, so make a call and visit that child. So 5, then simply print 5, and then return back to the parent function. Now 2 does not have any unvisited child, so simply return back to the parent function. And from this one, I will make a call to node 3. So simply print the node 3, and again return back to the parent function, and from the 1, I will simply return back to the parent function, which is a main function. Cool. So this is one DFS path. Now let's just assign a time in and a timeout value for every node. And I'm using a red color pen for time in and green color pen for timeout. Cool. So let me just first assign time in for every node, and I will start timer with 0. I will start timer with 0, and whenever I enter to the DFS function call, I will just simply increment the value of a timer and assign it to the node. So time in of 1. We'll discuss the purpose why we are doing this time in and time out very soon. So let's just first complete it. So for node 1, the time in is 1. Simply increment it and assign the value. Increment it and assign the value. So time in of 1. Also, let me write it over here. Time in, and yeah, these are the node. So DFS, or I can say the node values or DFS path. Cool. And then timeout for each node. So from the main function, I will initially make a call for DFS of 1, increment the value of timer, and then assign it to node 1. So time in of node 1 is 1. Then make a call to its unvisited child. So let's say we first made a call for node 2, and yeah, so this is the call for node 2, and again assign the value of time in. So increment the timer, assign the value. So simply time in of node 2, which is equal to 2. Then make a call to the unvisited child. So this node 4, and this is the call for the first time. So I will assign time in of 4. So increment the value of timer, and there exists a countless number of Euler tool for trees, but here I'm writing the best one, and you will get to know this very soon why this is the best Euler tool. So the first step, whenever you enter to the DFS function, increment the timer, assign it as a time in of a node. So incremented the value of a timer, and time in of 4, which is equal to 3. Time in of 4, which is equal to 3. Cool. So yeah, it is equal to 3, and then for this 4, we do not have any unvisited child, so start returning back to the parent function, and before returning back to the parent function, assign the timeout value. And for timeout value, do not increment or decrement the value of timer. Keep it as it is. So timeout of node 4, which is equal to 3. Super simple. And then return back to the parent function, which is a node 2. So currently we are at a node 2, and node 2 has one more unvisited child, which is 5. So make a call for node 5, and this is the call first time to the node 5. So assign time. So time in of 5, first I will increment it. So increment it to 4, and time in of 5, which is equal to 4. And for this 5, we do not have any unvisited child, so start returning back to the parent function, and while returning back, assign the timeout value, and do not increment the value of timer, assign the value whatever it is. So that value of timer, it is equal to 4, so assign 4 as a timeout value of node 5. So 4, and then simply return back to the parent function. So currently we are at node 2, and for node 2, it does not have any unvisited child. We have visited 4 and 5, and so return back to the parent function, and before returning back to the parent function, just assign timeout value for node 2. So timeout of node 2, which is equal to 4. I am not changing, incrementing or decrementing the value of timer. Whatever the value of timer, assign it as a timeout value. Then for this 2, simply return back to the parent function. So timeout of node 2, which is equal to 4, and then we are now at node 1. Node 1 has one unvisited child, 3. So make a call for this node 3, and since it is the first time, so increment the value of timer and assign it as a time in value. So timer is equal to 5, and time in of 3, which is equal to 5, and 3 does not have any unvisited child, so start returning back to the parent function. And before returning back, assign the value of timeout. So timeout of 3, which is equal to 5. I am not changing the value of timer. So timeout of 3, which is equal to 5. Cool. And then return back to the parent function, which is 1. And timeout for 1, which is equal to 5. Not changing the value of timer. And then return back to the parent function, which is a main function, that is end of our DFS function. Now this is the time in timeout value and the DFS path that we got. Now what are the advantage of this thing? So before discussing its application, here is the implementation. So the value of a timer, here is the implementation of one of the best Euler tool. There exists a countless number of Euler tool. It's totally up to you wherever you assign a time in value for the node, and whether you increment or decrement the timer value when you assign timeout. It's totally up to you, but this is one of the best Euler path that I know. So here I am setting the timer to 0. Here I am setting the timer to 0. This is the first step, and then this is our DFS function call, recursive function call. And here I am having a node and parent. The identity graph and this time in and time out arrays are considered as global. So time in of the node, increment the timer and assign it to time in of node. Cool. And here I'm just simply adding this node in the DFS path, basically this one, this system. And then iterate over it all its child, and if it is not equal to the parent, because we do not make infinite recursive call, then call this function for a child. And basically here I'm having a multiple parameter, but let me just quickly delete this one. Cool. So call this function, and before returning back to the parent function, assign the timeout value for the node. So timeout of node, which is equal to time. I'm not changing the value of timer. So these are only two steps which are important. So time in and timeout, where I assign the time in value and where I will assign the timeout value. Cool. So yeah, this is the implementation. Now let's see what are the application of this Euler path. Just use this. Now please try to pay more attention. Just use this time in values as the indices. Use these time in value as the indices, and then let's consider node 1. Let's consider node 2 instead of 1. So node 2, and what is the time in value? What is the time in value for node 2? It is equal to 2 itself. And what is the timeout value for node for node 2? It is equal to 4. So it simply says that from index 2 to index 4, I am using this time in value as the indices, and from this 2 to index 4, all the nodes which belongs to these indices within this range are the part of subtree of true, and that is true as well. That is true as well. So here let me just quickly draw it separately. So here I am writing the node. So node are 1, 2, 4, 5 and 3. Then time in values for node 1 it is 1, then 2, 3, 4 and 5. Then a timeout value, it is a 5, 4, 3, 4 and 5. And use these time in values as the indices. And to get the subtree of a node, just simply find its time in and timeout value, and this can be easily get with the help of this time in and timeout. So just simply say, let's say node 2. So time in of node 2, it is equal to 2, and the timeout of node 2, it is equal to 4. So from index 2 to index 4, all the node which belongs in this range are the part of subtree of node 2, and that is true as well. Here you can see 2, 4 and 5 are in the subtree of node 2. Let me just give you another example. So the another example, let's consider node 3. So consider node 3, which is a leaf node. So time in and time out both are same. So it means from 3 to 3, all the nodes which are belonging in this range are the part of subtree of node 3, and that is true. Only one node in the subtree of node 3. So yeah, it is actually this one. This 4. And let me give you a last example. Let's consider node 1. So this is node 1, and the time in of node 1, it is 1 itself, and the timeout of node 1, it is 5. So this means use this time in values as the indices. So from node 1 to node 5, all the node which belong is within this range are the part of a subtree of node 1, and that's true as well. All the n nodes are in the subtree of node 1. So yeah, this is the idea, and now I'm leaving this to you. Why this is working? Just find the reason why we are getting the subtree node whenever I access the range. So, and the intuition is very straightforward, because we are assigning the time in first, and then we'll make a call, and then I will assign the timeout value while returning back to the parent function. It's very straightforward. So yeah, these are the node in the subtree of 1, and now I have flattened this tree into an array, and we all know that applying operation over array is comparatively easier than applying operation over the trees. And yeah, this is the motivation for Euler tool. Now here are some facts, or kind of you can say summary of what I have discussed here. So flatten a tree to an array using a Euler tool, and operation on subtree converted to a range based operation, and range based operation can be easily performed with the help of various techniques such as segment tree, Fenwick tree, or prefix sum or suffix sum. Cool. So now let's just get back to our problem, and let's say we have flattened the tree. We have flattened the tree, and now we are given m queries. We are given m queries. We are given m queries, and for every query, there let's say there is a node u, and we have to delete the subtree of u, and then we have to return the two maximum node number in the remaining tree. So how I get this thing? So once I have flattened this tree into an array, and these are the basically node number. These values are the node numbers, and these indices we all know it is a time in. It is a time in values for all these nodes. So let's consider this case. Let's consider node 2, and time in of node 2. We all know that time in of node 2 it is equal to 3. Simply its index. So it is equal to 3, and here I am considering the timeout of node 2. Let's say it is equal to 8. So this means all the node in the sub in the from the index 3 to index 8 are in the subtree of node 2. So how I can answer this query, that is two maximum node number in the remaining tree. So this can be simply answered with the help of a prefix and a suffix max. For every index, just simply compute two maximum value in the prefix, and basically this is the prefix. Yeah, this is a prefix, and this is a suffix. So in this way we can answer the query in just a constant time. So this was the complete explanation for this problem, and let me show you the implementation over here. So this is the function, this is the method that you have to complete, and here first I am creating this graph, and basically tree, and all the trees are actually graph, and but not all the trees are graph. All the trees are graph, but not all the graphs are tree. Cool. So here I am having a array time in timeout, and here I am using this auxiliary array where I will store the DFS path according one base indexing, because everything is given as per one base indexing. Then this temporary vector v, which is for a DFS path and a zero base indexing. So then timer, which is equal to 0, initialize it with 0, is starting from the 0, and then I am passing this root and imaginary parent of the root, which is equal to -1, and then these are the required parameters. So here I am having a DFS function, exactly the Euler path function. So first I'm assigning the time. First I'm assigning the time in value for the node, and increment it, assign it. Then add the node in the DFS path. Then visits its unvisited child, and then before returning back to the parent function, assign the timeout value, which is same. Do not change the value of timer. Cool. And after this DFS after this DFS function, I have a DFS path in this vector v, because here I am adding the node. I am adding the node whenever I enter to the DFS function, and yeah, then I'm just simply converting it into a one base indexing, just to make the things easy, because everything is given in form of one base indexing. Then here I am for a precomputation of a prefix and suffix for each index. So the size is n plus 2, and why this plus 2? Because if we do not have a prefix or suffix, so then in that case my answer will be -1. So that's why I have initially added this -1. Then first and second, this is basically a simple prefix and a suffix precomputation, where prefix of I will simply store a pair, the two maximum value in left of it, including index I. Then similarly, suffix of I will simply store the two maximum value in right of I, starting from index I to n minus 1, to n, index n. Then here I am having this answer vector, then all the m queries, iterate over all the queries, and for every query, the node number will be given to you, and I will just simply say the time in, okay, this is the range, and time in value -1. So this is the range in the of the prefix from 0 to L, and this is the range of the suffix from R to N. Cool. And then here I am getting the first maximum in the prefix, then second maximum, then first maximum in the suffix, and then the second maximum in the suffix, and then I have just stored it into an auxiliary vector, and then I have sorted this in descending order, and the first two values would be my maximum, and which is the answer for the current query, and then I will just simply return this answer. So let's just try to submit this, and then I will discuss the time complexity. Cool. So successfully submitted, and the time complexity is linear because it's just simply a DFS call, and we are visiting each and every node exactly one. So the time complexity of this DFS function is linear, and we are also answering each query in a linear time because of the pre-computation that we have already did. So the overall time complexity is linear. It's basically n plus m, where n is the number of node and m is the number of query. So this was the complete explanation for all the four problems. And thank you so much guys for watching this video, and have a good day.